think it's recording. Is it going to come out reversed? It'll be fine. Okay. So I'm Turk, and I have to apologize in advance. I'm told that I use humor to deflect social anxiety. So I'm likely going to make a number of jokes that don't land during this introduction. I'm at the University of Illinois, where I'm actually not in I have a 0% appointment in astronomy. My full appointment is until, well, for the next 3 days, I'm an assistant professor at the School of Information Sciences. So I'm going to talk to you today about stories and YT. So those don't necessarily sound like they go well together, but I'm really excited to be here. I should have started with this. And I've never been to Scotland before, and so far it's been amazing. So, thank you for all you've done to make Scotland awesome. It's been really wonderful. And thank you for coming to the workshop. I really like these opportunities, like getting to meet with people and do stuff like this in an environment that fosters collaboration is a really exciting thing for me, and I just love doing it. So I'm gonna give you a little bit of an intro. Today I'm going to start by talking a bit about motivating analysis. And so specifically, I'm going to motivate why we do data analysis the way that we do with YT. But I'm also going to motivate stories. So this is going to sound a little bit weird, but I'm going to try to motivate everything we do over the next couple days with YT through the lens of storytelling. And you're thinking to yourself, oh, that sounds like he's not a serious person. But I promise you that, in fact, I am a serious person, or at least that I'm going to pretend to be. I'm going to use this as an intro to the philosophy of stories and why you should care about that as we move forward. And then we're going to get right into using YT as a tool. And we're going to load up some data. And I'm going to talk to you about the way that YT thinks about data and why we do the way that we do. But again, I promise I'm a serious person who does serious things. Okay, so I know that the more I say that, the more you believe it. I work in information science, and there's the joke. I don't know if they have that, if the joke is like worldwide or if it's just in the States, but if you have to call it a science, people think it's not real. Anyway, computer science, data science. So by training though, I'm a computational astrophysicist. So I did all my thesis work and my first 2 postdocs as in computational astrophysics. And in fact, I in the course of that, I developed simulation tools and platforms and whatnot. And I worked on platforms. I didn't really develop the platforms, but I did development on them. And I worked on analysis tools and whatnot. And now I sort of work in interdisciplinary applications, and I've worked a bit on studying communities of practice and open source scientific software and so on. Although I'm not sure that that's exactly where I am right now. And I'm tenure track for the next couple of days at the School of Information Sciences, developing and implementing a grammar of volumetric analysis. So the idea that you can apply these operations to data that is organized along volumes, and we can understand the way that the operations can be conducted and how they are specifically applied to different organizational schemes of data. So, but let's talk briefly about stories. Okay, so stories and visualization. We ask ourselves, what does visualization accomplish for us? What is the purpose of taking data and turning it into it? And then why is storytelling important in visualization? Why should we care about this? And why should you care about it when you are just trying to figure out, some figure of merit for a paper? But then in order to answer that, we kind of have to ask, what is visualization and how do we visualize, tell our story, blah, blah, blah. What does it mean? And so let's quick center ourselves, though, before we get too far out there. And I'm going to tell you a story about how I got here. And in a sense, it's also a story of how you got here. We're all protagonists of our own stories. So let's take a cartoon history of the universe. One of my favorite lines from a cartoon in the 1990s was something like, oh, they're going to destroy the Earth. Oh, no, that's where I keep all my stuff, right? So the universe is where we keep all of our stuff. All right. So after recombination, the universe was nearly, but not totally homogeneous state. It was seeded with instabilities, few residual electrons, and so on and so forth. And then, broadly speaking, early on, dark matter clumps formed and collected halos. They drew in baryonic material and so on. And this process converted potential energy into thermal energy. It heated baryonic matter. And then it shed that thermal energy through radiative processes, right? And then eventually, this cloud then and becomes molecular three-body interaction, forms a law, and then it's formed. In any environment absent heavy elements, the mechanisms by which gas cools are pretty limited, and the principal coolant is molecular hydrogen. And it forms first by electron association, and then through three-body interactions. And so, if we think about this is basically three atoms. Blammo! And then, it spins off, right? One acts as a catalyst. And then it heats the gas by roughly 4.5 eV per molecule. So this is what I spent most of my thesis work sort of studying. Okay? And the way that I came at this was trying to understand the way that these different sets of processes and operations interacted and how we could characterize them when they weren't necessarily the specific things that were identified in my simulation. Some of these were like the exact values of these, but if we wanted to be able to characterize the stability of the chemical formation channels, if we wanted to characterize the various different timescales and so on, that was all different things that needed to be derived and compared and analyzed inside different mechanisms. And so stepping back, in order to look at these different processes, we have to visualize data in some way, whether that visualization comes down to turning it into a single number, that characterized the stability or the instability or the time scale of various different things, or whether that was looking at distributions, which required a spatial character or a spatial component to them. We had to take this information, transmit it to our eyeballs and then to our brain and so on. And to do so, we had to visualize. But visualization is a process of lying. Okay? This is the key part. Visualization is a lie. We have to tell lies in order to visualize. At the very basic level, we've got something like 6 times as many rods as we have cones inside our eyeballs and something like that, and so there are different ways that we all interpret data that it gets into our visual cortex. And all of them are reductive methods. So in this sense, we are always lying through omission when we visualize data. Even if we're showing a slice plot or a projection plot, or if we're showing a phase plot, something like that, and we've got one pixel per every single thing, we are applying a reductive process where we are stripping away information and then transmitting it to our eyeballs, and then that gets interpreted. So we have to tell these lies. So as an example, of course, everyone's seen you know what? Let me get through some of this. I'm getting self-conscious about this whole like telling stories, but if we were to break down a sentence like the sky is full of stars that twinkle, we break this into different components. The sky is full of stars. Stars twinkle, right? See, can we twinkle? Oh yeah, they're twinkling. See, we watch National Lampoon's Christmas Vacation every year, and there's like a line in that where Chevy Chase's wife says, and I forget the actress's name, Beverly. Anyway, she says, "Yeah, they're twinkling. The little lights are twinkling, Clark." Anyway, this is the inverse process of visualization, where we're taking some reductive operation, and then in our brains, we're constructing an image of what it might look like. And so this is the inverse process, but it's that unification of the forward and the reverse processes that we're trying to experiment here, where we want to be able to construct some characterization based on a visualization. And so, strictly speaking, some people like to divide this up into the notion of data build, on top of data, you build knowledge, on top of knowledge, you build information, on top of information, you build wisdom. And the idea is that this DKIW hierarchy allows you to specify at what level you have different degrees of understanding of the information system. If we think about visualization from the perspective of an astronomical phenomena, of course, there are probably multiple people in the room that could explain better than me why this is not an accurate representation of the actual underlying data. But we can start with the fact that it's not what it would, look like to a human eye, right? This is a false color image where different channels are, applied to different things. But we wouldn't necessarily think about this as a lie in the sense that it still is representative of the data. But in another sense, it is a lie because it is utilizing channels that we are accustomed to in order to express data that is not necessarily aligned with those channels. Okay. I'm going to move forward through into this, beautiful picture. We've all seen clouds and things like that. If we motivate our simulations from the perspective of wanting to be able to understand them, we've got a set of equations that we apply inside an astrophysical simulation, and then we can evolve them over time. And then sometimes they look like what we see and sometimes they don't, but that inverse problem is where things get a little bit sticky. And these are all the different processes that we basically want to go through with simulations. We want things to look like we expect them to. We want to be able to understand them and query and mine them information. But what do we actually do when we are conducting analysis? So Sam Walkow was a student that worked with me, and I like to show the work that she did, where what she did was she worked with different researchers to try to understand how individuals construct the stories of their data. How do you sit down with a simulation and then come out of it with information about what happens? How do I start with a gadget data set and then come away from it saying that this is how star formation is quenched in galaxies, right? And it's typically an iterative process where you start out with some sort of a hypothesis or at least some sort of gut feeling of what's going to happen. And then you run simulations, you attempt to query them for the things that you expect to find. And then this becomes an iterative process where you then either rerun the simulations or rerun your queries. And what we want to do as we move forward during this week is, well, we want to avoid having artifacts that are quite as obvious as those. Like, see how we're getting a real nice square. Expected that joke would land better. Like, that's a super ugly simulation, right? You see how, yeah, super strong axial effects. There we go. So anyway, typically we're going to be in a situation where we iterate over things. We iterate through our process. We attempt to identify new queries, and then we feed those back into our next set of queries. And throughout all of this, we are telling ourselves a story, right? From a narratology perspective, and I know you're thinking, oh, I didn't sign up to hear about stories. Is you relevant? From a narratology perspective, there's what's called a storytelling triangle. And this I'll borrow from Kate McDowell's framing. But basically, there are three components in any story. There's the storyteller. There's the tale that is being told. And then there's the audience. And when we go through the process of conducting analysis and visualization of our data, we are at different stages building out the relationship between each of those three things. Because when you tell a story, whether that story is data that you are, or the story that you are telling yourself about your data, the story that you are telling your colleagues and your peers about your data, or the story that you're telling the public about your data, you're building three independent relationships. You're building the relationship between you and the story or the data itself, your understanding of it. You're building out the relationship between you and the audience. So me telling you about the way that stars are formed in the early universe. And then you are building out the relationship between the audience and the underlying data itself. I can't believe I timed that so perfectly. Because when you leave that relationship, you leave behind this relationship between the person and the information that they've absorbed, the knowledge that they've absorbed, and so on and so forth. And so if we understand the way that you relate to your data, then we can better shape your ability to communicate to your audience and then your audience's ability to retain that information and take it away. So if I'm constantly thinking about my data as a set of HDF5 files on disk that all overlap in different ways, and I add layer upon layer upon layer that removes me from my connection with that data, that just adds more and more technical friction and file system specific things between me and the data, I'm no longer able to relate to it in the same way as if I apply largely physically motivated analysis to it. Okay. Basically, these are visualizations we make for ourselves, our peers, and everyone else. And then I'm going to go ahead and I'm going to skip here. But throughout this week, I want you to think of the visualization analysis that YT does as not a strict subset of making an image, because it also includes the collection and organization of the data and the representation of that data. Let me skip ahead. And the second one, the tenet is we have to tell lies, but we have to be honest, because no visualization can fully reflect the complexity of a data set, and some representations are better than others. Let me go through here, blah, blah, blah. I'm going to show a visualization that we made with YT. So this was a visualization we made. What the heck? If I do it on the lecture notes, it doesn't do over here. This is a visualization we made with YT where there are good things and bad things about it. But I want to show it because there are some very specific things that were enabled by our utilization of a physically motivated analysis package. So this is an isocontour of a deeply nested AMR simulation. And then what we did was we applied isocontours at several different stages of chemical reaction dominance. So each one of these isocontours, as we go out, and I think at this isocontour, I transitioned them to just being in like log space. Each one of those internal isocontours is at a different stage of when different reactions, molecular hydrogen, become dominant, when different cooling reactions become dominant, and so on. And then for the second half of the visualization, what we did was we applied, roughly speaking, a thermal black body radiation for the colors, and then density weighted emission. So this is, in principle, a physically meaningful visualization. But here we're not doing isocontours anymore. Now we're doing, continuous emissions with a transfer function. Now, there are also a lot of problems with this visualization. And so typically I show this visualization when I teach my data viz class, and I say, now you've got 5 minutes to discuss amongst yourselves and dunk on it in all these different ways. And then, people do, and they say things that really hurt my feelings, but I pretend that I don't. But there are problems. Like, for instance, that first part, if you're not expecting, if you don't come into it understanding the visual language, you might think that it's collapsing when really the camera is moving because the frame of reference is not very clear, and especially because it turns. Whoa. Yeah, that's me. All right. So moving away from my YouTube recommendations, there are problems with it, but ultimately, we try to be honest with it. We try to be deliberate, informed, motivated, and justifiable. That's what we're going to work on during this workshop. So let's talk about YT. All right. I'm off my nonsense. So how can we think about analyzing astrophysical data from a spatial, or how can we think about analyzing data from a spatial perspective? Essentially, YT applies a vocabulary of data analysis that can roughly be broken down into 4 different categories. There's the registration of data, and I'll explain registration in just a minute. There's the transformation of data. There's the selection of data, and then we have the reduction of data. And these 4 things are basically the 4 operations that YT does. And ideally, this top one doesn't happen explicitly. And that's what Britton was alluding to. The idea of the registration of data of putting things where they belong in a spatially organized sense is something that happens transparently. In many ways, there are a number of different transformations that are applied transparently. Selections are things that you do explicitly that it manages for you, and then reduction is typically where you step in and you do things. So if we think about this, registration is the notion that we have data that is distributed on disk in some manner. And the way that it's written out on disk may or may not correspond to any kind of spatial organization. It might be spread about through HDF5 files. It might be in a SQL data. Oh, I couldn't even get that out. It might be in a SQL database. It might be spread out among unformatted binary. It might be in any number of different ways. It might even be as a series of vertices and edges and faces. It might be higher order finite element. It might be any number of different things. The one that I like the most, though, is when you think about like MRIs. So when you've got a brain scan, my understanding is typically inside the nifty file format, they include things that typically they're stored in a registered way such that they conform to like this reference model of a head, and then inside it they've got affine transformations that describe how to transform it back into whatever our lumpy heads are shaped like. But you've got data that is distributed on disk that may or may not correspond to any type of a spatial organization. And the first step is to construct this into a logical organization that is indexable. And so that might look something like this, where you've got, similar to what Britton showed, it might be, something like this. But this is also just a logical indexing-based system. This is where you have things that are next to each other in conceptual space or for indexing space, but are not necessarily next to or that are not necessarily shaped in a rectilinear way. So they might also be they might be registered, in a cylindrical or in a spherical format or something like that. That is represented by that logical indexing organization. But the key thing here is in registration, what we have is we develop an f of x, where the f of x is a way of taking a vector in space and then saying this is what the value of these different things is at that vector. So for instance, inside this room, we have all these different people. We also have microcurrents everywhere. We have coffee smell that's distributed throughout the room and so on. And if we had a registration of data, it would allow us to query what each of those different values is at each different location, right? And grid-based decomposition is one way of doing that. It is not the only way of doing that. For instance, sometimes we might be in a situation where we have samples of Lagrangian particles or something like that that are maybe laid out in a completely different way, but by applying a registration system to them, we retain the ability to compute at any vector inside that domain what the value of different fields are. And so this is the really key part here, is that if we are able to say that we have a mechanism of computing the value of different fields at different locations inside our domain, then all of a sudden everything else kind of falls into place. If we're able to say that inside this room, we can query at each individual location and compute the local density of fans of Marvel movies or something like that, then all of a sudden we can compute an average over the volume, right? Now it's subject to sampling and things like that, but we can still compute it and we can apply bounds to it and we can come up with all these different ways of applying it. And as soon as we have a functional form for fields inside a domain, we can start to apply transformations. And this is where things really open up. So primitive variables are those that are often stored on disk. So that might be, for instance, my velocity in the x dimension and my velocity in the y dimension, right? And so that here, it's clearly, taking, I've got these values that I'm sampling. And so if you are able to compute the velocity in the x dimension and the velocity in the y dimension in something, then all of a sudden, you can also compute the velocity magnitude, right? Now, this is not something that gets stored on disk. This is something that can be computed at any given location. And so if we are able to query the value of a field at any given location to begin with, and we have this set of primitive variables, then all of a sudden we are able to compute on the fly the value of anything that has arithmetic or spatial operators applied to it. Now, this is an example where it's just very, very simple arithmetic operations, but more complex examples such as divergence, curl, gradient, and whatnot can also be computed as soon as you have the ability to query fields at individual locations. Now, the next stage in applying these different things can be selecting variables or selecting subsets of the data. So Britton used the example of a sphere, and I was thinking about it, your example of a sphere. I think there is a redshift at which, if you have co-moving megaparsecs and proper kilometers, it actually would work. So we need to think about that, I think. So I don't think your units, yeah, run the numbers on that.
Thank you.
So you can imagine having some sort of a selection that is applied based on, say, connectivity, spatial organization criteria. And at a very simple level, that might be something like, selecting just this region right here, selecting this region right here. And here, let's see, maybe I just want to select this region or this one or something like that. Here, let's drag this. And so you can select subsets of the different regions. And then you can apply those subsets and calculate on those subsets and so on, and then apply your transformation. You can compose these operators in some way. But you can also, if you have a selection criteria that is defined rigorously like that, you can also apply reductions along axes. So let's imagine now that we wanted to apply some sort of a query along an axis. We already have the ability to compute any given field at any given point. We can also now apply selections around something. We can now apply transformations, so we can compute, say, integrating along along the gradient or something like that. So we can now, in principle, see if this. Oh no, I got to click down here. Let's go. You can imagine now being able to do things like compute along some sort of a path that passes through your simulation. So in cases like this, you can apply basically any type of a non-trivial manifold or path or something like that. And you can query along it, compute values, accumulate, and so on and so forth. And this also works along, for instance, time in the sense of something like Y-tree, which I think Britton is going to talk about later on, where you can watch individual halos evolve. You can watch changes in data sets over time. And then finally, building out of all these different reduction operations, we can compose different operations. And so this is where we get the ability to take a data set, look at connectivity of particles, look at field values inside those, inside some sort of derived quantity that we get out of the connectivity of those particles. And then we can compose these different operations to compute the way that, say, halos form in the universe. So we might have our data set distributed randomly on disk. This is a Ramses data set. And then, we turn that line noise into a nice, pretty picture of the cosmos. We apply reduction operations onto it in order to identify the regions where there are, say, halos of dark matter. We then apply operations on each one of those individual halos in order to compute the, say, the virial mass or something like that. And then we take those and we re-register them in a completely different environment in order to come up with a mass function, which I've helpfully not labeled the axes on. How do we do that with YT? So YT, does anyone know what YT stands for? What?
Yours truly.
It is, yes, it's yours truly. Do you know why it's called yours truly? Has anybody read Snow Crash? Well, then I won't bother. I mean, it's like an in-joke from an old book, so whatever. So YT is a boundary object. It exists between you and between the data and the semantics. It turns, and semantics here is not a pejorative like I use when like I'm arguing with my kid. It's a boundary object that exists between you and the data in order to help you build out your knowledge, understanding, and wisdom around the data sets. It's largely written in Python and Cython, and it was originally designed to read strangely formatted data from AMR simulations generated by the code Enzo, but it's moved far beyond that, and I'll talk about ways in that. With Enzo, for instance, it would read from these CPU files, for instance, that had all this information packed in and that needed to be reduced and so on. But it reads from several dozen different data formats, and then and actually Chris has done a lot of work on expanding the loader operations to read from just about anything. And then it applies it into it takes that data, turns it into a memory model, and then it applies semantics to it. I'm going to talk first about particle data sets when I pull the notebook up in just a minute. The model is the data is indexed, read in only as requested, and then accessed with respect to physical coordinates rather than computationally oriented systems. The first code that we supported other than Enzo was a code called Orion, which was written by a group out at Berkeley based on something called boxlib. Enzo liked to keep everything close to 1. So it would normalize the length units, the density units, and so on by dividing them by some obtuse set of constants in order to keep them all close to 1. Orion liked things to be in CGS. And so Enzo would load things in, and I had a cosmology simulation. It would run from 0 to 1. Orion would load things in, and they'd be in centimeters. And so it'd be much, much bigger. And so we first realized we needed to be able to access these things with respect to physical coordinates if we wanted to be able to do any meaningful access, meaningful comparisons. It makes visualizations, has some astro-specific modules. It also has some non-astro-specific modules that Chris has worked on quite a bit. Oh, I should mention, the reason that Chris is sitting in the back and the rest of us are sitting up front is that he's a geophysicist and we're all astronomers. So what does that all mean? It means that we have the ability to do data format independent analysis and visualization. So this was a visualization courtesy of John Zuhone and I shouldn't have said which is which because I should make you guess. But Gamer2, Arepo, and Gizmo data outputs all next to each other. And so Gamer2 is block-based AMR. So I think formally it's like octree with leaf size of 16 or something. Arepo in the middle for adaptive Lagrangian Eulerian, and then on the right is Gizmo. So you can't call a Gizmo SPH or you get yelled at. It's meshless code. Am I right? I can't call it SPH, right?
It's not SPH.
Right. So I'd get in trouble. I'm already getting in trouble.
Trouble, man.
I know. Yeah. So YT is a substrate. It's on top of this that we build plugins for doing synthetic observations like Trident, which Britton can tell you about, Powder Day, which I think Ramil has used a fair bit, right? Ish, maybe not. PyXSim. Then there's interactive, web-based visualization, astroanalysis, Y-tree, and so on. The idea is that once you've ingested data in, all of the operations that are applied to it are nominally independent of the type of simulation code that has been used. So let's get into it. Thank you. I always have to put thank you at the end so that I know that I'm done. There are no minutes. So thank you, and also because I'm grateful, but thank you, and let's get into it. So what I'm going to do is I'm going to load up a Jupyter notebook, or Jupyter Lab, and I'm going to work with you on learning about how YT indexes. Dang it. There we go. Okay, so ignore this stuff. I'm gonna, dang it. There we go. Okay. So we're gonna get started here. by loading up Jupyter Lab. Has anybody not used Jupyter before? Does anyone know? Can't spell Jupyter without YT. I said that to Fernando Perez once, and he thought it was funny or pretended to at the time. Has anybody not used Jupyter before? It's okay if you haven't. Really? Even you?
I've used it. I know, believe it or not.
Okay. So I like Jupyter Lab. You might use Jupyter Notebook. It's fine. I know now they've rewritten it so that you can do one or the other from the same backend. But we're going to import YT. And I'm going to assume that folks are a little bit familiar with the way that we do Python stuff. And I'm going to import it. And I want to point out, did you see how fast that was? That is all thanks to Clément. Clément has had a quixotic, is that the word I'm looking for? Quixotic goal of improving our import speed, and it's actually gotten considerably better.
Actually works. So product data
What?
works, right?
Oh, so quixotic is not right?
Yeah.
Wow. First
Quixotic,
I say gizmos, not SP. No.
my computer dictionary says quixotic is exceedingly idealistic, unrealistic, and impractical.
Actually, I think it does work.
That's me.
Yeah. And so we're gonna load that in, and actually, I'm gonna get rid of this. You don't have to type these things yet, okay? Because I'm using the sample data sets. And I wanna, here, let me pull up my notes, real quick. So YT presents an API, and you get to choose the degree to which you engage with the API. It has a high-level API, but it also has a low-level API that allows you to access the underlying data objects. So for instance, if you need to do debugging of your simulation, it also makes that information available to you. For the most part, I'm going to show how to do the high-level stuff rather than the low level, but both are accessible. Okay. And the other thing that I want to mention, and I took all these notes and then I just totally ignored them. One of the first things that I struggled with when I was learning Python was I'm young. This was a long time ago, before we had NumPy, before it was the one thing that it is now, back when it was still numeric. Before NumArray came around, and then there was the weird merger that turned into NumPy. And oddly enough, like if you ever go back and read the histories of that stuff, it's really interesting how deeply involved astronomy was in all that, especially Perry Greenfield with the development of the early numerical things, and physics too with David Beasley. Arrays are really important, and I didn't really understand that when I first got into Python. Because I thought, who cares about arrays? What's the point? The first stage I had in understanding arrays was when I realized that they improved performance. Because all of a sudden I realized, I don't have to iterate over this list and I get to do all these different things. And that was like the signal to the CPU. Everything is going to be basically the same. You can just do these operations. There's no boxing, unboxing, coercing of data types and so on. But the real value of arrays, which I hope comes across here, as we move on, because we're going to talk about how to think about data sets higher level than arrays. But arrays became really valuable to me when I realized I didn't have to think about iterating at all. I could think about summing things up and just call sum on an array. Or I could call mean on an array and I could get values back from that. And that was like a huge thing. I no longer had to do total equals total plus a of I. I could do total equals a dot sum. So I'm going to walk through what happens when we load a data set into YT and yeah.
You should maybe point out that these will work for everyone regardless
Oh,
of
yeah.
whether they've downloaded data.
Yes, this will work for everybody. They are kind of big though. So if you don't want to do that and you want to do it to one of the sample data sets, that works too. Right? Some of the operations may or may not. I'll get into it when I do it. I'm going to sit down if that's okay. Do you think it's going to work?
Yeah.
It worked. I mean, I can get the chair. All right, and if it's okay with everybody else, I'm also going to go back to mirroring my display. So one quick question, is this text big enough? Okay. All of this will be available in the repository. I'm going to load up a sample data set. And the sample data set I'm going to load up is snapshot 33, which is an Eagle data set. And so it's not the newest, but it's a pretty cool SPH data set, like actual SPH. And it also, but it uses the OWL's ion fields. So we're going to load this up. Now, what we have is we have this, I guess it's an OWL's data set. We have an OWL's data set. And so that was really fast, right? I mean, you don't have to say it was really fast if it wasn't, but I think that was legitimately pretty fast how it loaded it up. So this process of loading a data set is designed to be very lightweight. It won't be fast for you if you're downloading the data set, but the second time you run it, it will be. It's designed to be very lightweight because we wanted to optimize for the case that you may have many data sets that you want to select from. So the idea being that you load up multiple data sets with hitting the disk as few times as possible, and then develop which type of, or which specific data set you are interested in based on, say, their parameters or their metadata. When the data set is loaded up, YT reads in metadata from that data set. That metadata might include things like when was it generated? It might include things like what were the parameters of the simulation? It might include things like, if it's a cosmology simulation or not, if the cosmology simulation is of a particular size, what the boundary conditions are. It might include information about units, and it might include information that YT doesn't know about. Okay? In fact, it will include information that YT doesn't know about. There are two different classes of metadata that YT parses about data sets. The first one is things that influence its operations, and the second is everything else. So for instance, inside DS0 in this case, if I do dot parameters, that is everything that YT is able to grab from the metadata. And not only is it everything that YT is able to grab from the metadata, ideally, it is also in the format that most closely resembles what is available on disk. So all of these different things use the terminology of the simulation code, which is not necessarily the same as the terminology that YT might use. So here's an example of that. Here in the simulation code, it says omega baryon. You see it's capital O, capital B. YT has an internal name for that because it can influence some of YT's operations. And I guess YT doesn't do baryon, it just doesn't matter. So omega 0 turns into omega matter, okay? So there's the stuff on disk that's simulation specific. And then there are the higher level things that YT interprets. So now if I load in ds1 equals yt.load sample Enzo cosmology plus. I thought I had that one downloaded. You all sipping through the same straw?
Right, you import numpy, is that?
I didn't yet.
What's the NP then?
So that is NumPy, but I didn't import it into my local namespace. YT did though. So internally, YT has imported NumPy.
So,
Yeah, but then I'll need to do that myself up here if I want to access NumPy operations. So I'll do that. Okay, now it's speeding up a little. Everybody else is downloading, right?
Accelerating.
Still, I'm gonna interrupt.
Yeah.
I think I've got one.
You have tiny
I
cosmos.
think I do.
That's basically the same stuff.
Apparently I don't. See, I changed it up at the last second to use that instead of the. All right, we'll do isolated galaxy. Okay. So DS1 now also has omega matter. It's set to 0 because it's not a this example is bad. That's why I wanted tiny cosmology or endocosmology plus. But DS1 has omega matter. But if we look in parameters, it's called something different. Okay. And so the key thing here is that there's the stuff that exists out there in the parameter set, and there's the stuff that YT interprets. So you can assume that anything that YT interprets will be shared amongst different data sets from different types of simulation code. But you also still have access to the superset of information that is specific to your data set. The idea here is that there are some things that we all share and other things that are different, and we want to make access to both accessible, available. So let's take a look now at DS0. And this is my OWLS data set. YT distinguishes between the data set, which is information about the data, and the index, which is mechanisms for connecting where the data exists spatially with where it exists on disk. And the index is not constructed until requested. Indexing can be a somewhat lengthy process. There are ways of accelerating it. We also do, in some cases, store information in between runs in order to do that. But the index itself is not constructed until requested. So if I do, and it will also be implicitly requested at various different times. So don't worry about, you never actually should have to do ds.index. I'm doing that to demonstrate. It loaded my particle index off of disk. So the way that YT thinks about different data sets, different types of data is different. So for particle data sets, it has what's called a particle index. The particle index itself, and we had indexes on the list for my talk, but the particle index is built on what's called an enhanced word-aligned hybrid system of storing information. So you can imagine that maybe there are different ways of storing data for particle data sets. Maybe it's randomly stored, maybe it's sliced, maybe it's stored according to a Morton curve, according to a Hilbert curve, or something like that. But when you want to select from a discrete data set, you want to be able to identify which files need to be queried in order to get that sub-selection of data. There are other cases where, as you select a given region, you might need to be able to select its neighbors very efficiently. What YT does is it stores a set of a single level hierarchical index. So it takes the particle data, it computes its Morton index into a bit field, and then anywhere multiple files intersect so that you have multiple files that contribute to the same area, it does a more refined indexing on that. So the whole idea behind this is that it travels over all the particle data sets one time. It figures out where each one contributes to inside your spatial organization, and then it stores it for the next time. For the most part, you don't need to know about any of this unless you're running into performance issues, in which case you can tweak what's called the index order. And so here, the index order for this particular particle data set was heuristically defined as 6, so 2 to the 6 cells for the coarse index, and then an additional 2 layers, 2 levels of binary subdivision on top of that for the fine index to reduce collisions. And so what that allows us to do now is we've got DS0. We can access it with, let's say, the R operator, and I'll do access from, you know what? Let's take a look at some of the other metadata. So we have a domain width associated with it. Oh, I've got widgets installed, and so you'll see it comes up here in code length. Let me zoom in. And in code length, it's that, but here in centimeters, it's like 1 × 10⁻²6. Or if we look at it in megaparsecs, oh, megaparsecs aren't in here, but parsecs are. You know, it's that many parsecs. KPC, yeah, KPC co-moving. So 34K KPC co-moving. So we can select from that. Let's do a sphere centered at the center of the domain. And let's say that it is 100 KPC co-moving in size. You see that returned it very quickly because it doesn't read anything off disk. We have a sphere. There is its center. There is its radius. And we can now access a field from that. So up to this point, if we hadn't already constructed the index, it would not have indexed the data set. It's at this point when we actually ask for data from disk that it would do that. We can get ones. So this is 1 for every single particle inside that selection. So this next part, I don't want you to do. I'm going to show you a little bit about what it's doing on the back end. So here it has the way that it works for particles is it has individual particle containers for every file that overlaps with it. And then it has start and stop locations in that file that it reads from. It chunks those files, and so it attempts to identify the minimum amount of data that it needs to read from disk in order to get that information. Now let's take a look at what happens if we do that with an ENSO data set. So here, this is DS1. This is my isolated galaxy. I can do DS1, and I'll do a sphere here, center of the domain. And we'll do 100 KPC. It indexes by parsing the hierarchy. Now, if I look at SP, I only get a couple data. I get that many values. So it's doing the exact same thing here. It identifies which files those grids live in, and then it reads those from disk, but only the amounts that it needs. So Britton's going to talk about data objects. I feel like I should talk a little bit about.
Yeah, that's fine.
Fields. You're not doing fields in detail.
I'm doing on disk fields.
So I'm going to show you a little bit of what our data set might look like. So we have a list. No, this is what you're supposed to talk about. Less time to talk about parameters than our data sets.
That's all right. Coffee's here.
So
So we can,
and you also started, you didn't go long enough.
no,
No, I've been going for,
you've actually gone the right amount of time.
I've gone the right amount of time. Okay, thank you. Okay, so we're going to take coffee break now.
Yeah.
But here's the takeaway from this morning. Blah, blah stories. Data sets are cheap, indexes can be more expensive. And that allows us to do quick accesses of our data and selected and targeted reads. Okay.
Great. Thank you, Matthew. Well, we have coffee just outside. We have a little bit extra, but let's meet back here at 20 past. I think that works. And when we come back, we will load in some new data and start actually getting data from disk and seeing what we can do with it. Okay, great. Thanks.